Hello, welcome to another little talk here. So I hope this example helps you. We're going to start chapter 2.1 now, Introduction to Second Order Linear Differential Equations. And hopefully you've looked at the text and read through it, and you'll see that the form of a second order differential equation I have indicated here. So the idea is that I'm going to do this example number 11. I'm going to try a different technique here. I have actually worked out the problem, and as I'm talking, I'll try to bring attention to some of the things I'm talking about. So we're looking at this number 11. So right here, let's see if I can get this going. Oh, crud. That on there. Close tabs. Okay, so here we go. So I'm going to pick my color here, something you can see. There we go. So here's the question, number 11 from 2.1. So we're trying to, I guess, let me read this, solve this differential equation. And we have sort of these general techniques that we're starting to study in 2.1 for linear equations. Okay. So here we go. The question is to, let's see. Okay, in this problem we have a homogeneous second order linear differential equation. We have two functions, y1, y2, and a pair of initial conditions, it says here, are given. It says, first verify that y1 and y2 are solutions of the differential equation. That's number one. And then find the particular solution of the form y equals c1 times y plus c1 times y2 that satisfies the given initial conditions. Okay, so here's our differential equation. And if you've read the chapter, you know that since it's the second order differential equation, we need to find two linearly independent solutions, and then we can solve the initial value problem that is stated here. So, all right, the first part I'm doing here, right here, I've written down the first proposed solution, y1 and y2. So what we need to do is try to determine whether it satisfies this differential equation, which I'm calling, I guess, star. Okay, so we need to use the product rule to find the derivatives first of the two functions, and that's what I've done here. Okay, and then we need to find the second derivative, and I've done that here and here. And I recommend that you look over that and make sure that you understand how that occurs. Then proceeding, I'm going to verify that, in fact, both of these functions, or I guess I'm going to verify that y1 satisfies the differential equation in the second step here. So what I write down is, in fact, I have, so I take the second derivative of y1 minus 2 times the, little error there. That's supposed to be the first derivative, okay, of y1. Plus 2 times y1, that's supposed to be 0. So what I do is I check to see that that's correct. Right here is what I calculate to be the second derivative. And right there is what I calculate to be the first derivative. And I'm adding 2 times that. And let's see, what did I do? Oh, I guess I made a mistake. So this is the second derivative right there. The minus 2 times the first derivative is the stuff inside of here, right? Plus 2 times the function itself. And if you do the calculation, as I have done here, you see what you get is 0. Okay, so that shows that the first function is a solution to the differential equation. And similarly, you can check the details that the second function is also a solution to the differential equation. All right, now what we want to do is we want to solve this differential equation given the initial conditions that we know that the function at time t or x or time equals 0 is equal to 3, and that its derivative is equal to 13. And so what we do is we simply write down the following. We know that the general solution of this differential equation is given by this, is of this form. It's the linear combination, as we say, of the two solutions, assuming, of course, that they're linearly independent. So now what we're going to do so y is equal to c1 times e to the x cosine x plus c2 times e to the x times the sine of x for some numbers c1 and c2. Okay, so now we're going to use the conditions. And in fact, as you can see, I wrote down the wrong conditions here. I guess we want to have okay, y of 0 equals 0 and y prime of 0 equals 5. So that's what you're looking at here. So what I need to do is first write down what y is, calculate its derivative, okay, using again the product rule on both of the functions. And then in fact, plugging in 0, so the first condition is if I plug 0 and I get 0, but we know that if I plug in 0 I get, for example, the cosine of, what am I doing here? Hold on. So the cosine of 0 is 1, that's what you're looking at here. E to the 0 is 1, and then you see the C2 term dies off because, in fact, the sine of 0 is 0. Using the second condition, as I'm doing in this line right here, you see that when we plug 0 into the derivative, we get 5. Okay, so again, the first term, if you look at it here, we get an occurrence of the cosine here. Okay, and then the sine drops out. But we also, over here, we get a 1 here because we get another occurrence of the cosine here. So this gives us a system of equations that you're looking at right here that we will solve using, any technique that you would find appropriate. And the system of equations is, in fact, right here. Well, if C1 is 0, then using that fact, we can see that, in fact, C2 has to be 5. So the solution to the particular solution of this differential equation is right here. Okay. Next one I'm going to do is problem number 25 here. The question is, determine whether the pair of functions in problem number 20 through 26, it says, are linearly independent or linearly dependent, okay, on the real line. Okay, so, all right, let me say a little bit about what this means. So there's a very nice definition in your book about linear independence and linear dependence. And this term will come back, and we'll be very interested in utilizing this terminology in the future. But essentially what linear independence means is the following. If you have, let's suppose that you have n vectors or n objects. Maybe in this case we have 2 objects. And we're trying to determine if they are linearly independent. Okay? Essentially, we want to know if any one of these functions can be written as a linear combination of the other functions. Okay? Now, another way of stating that is by writing down the equation. 0 equals, and then we take C1 times, so here, let me do this underneath here. So the general principle is this. You have these objects, maybe they're vectors. Actually, maybe some of you have heard of vectors, V1, V2, V3, out to, let's just go to V4. Okay, so we have these 4 vectors, and we would like to know if they are linearly independent. So what we do is we write down this equation. We say 0 is equal to, now that we take some constants, C1 V1 plus C2 V2 plus C3 V3 plus C4 V4. Okay? And we ask ourselves that whether or not there are constants C1, C2, C3, and C4 that are not all 0 that satisfy this equation. 0 equals C1, V1. Okay. The reason this is the this equation where they are not all 0 determines what we call linear dependence, Because in the event, let's suppose that that C1, let's suppose that C1 is not 0, okay? Well, then look what we can do. We can say, oh, in that case, I can write down V1 is equal to C2 times, V2 times C2 plus V3 times C3 plus V4 times C4, and I can actually divide by C1, okay? So this is a way of defining what linear independence is. So the idea is that when we have things that are linearly independent, the only way we can write down this equation is when all of the C's are 0. And then that eliminates the possibility that one vector, in particular, in our example of V1, is a linear combination of the other vectors. You may think of it in the following way, that if you have linearly dependent vectors, that is, you may have at least one more vector than you need to express the other ones. So that's a very bad explanation, but let's look at it. We'll see this over and over and over. We'll see this over and over and over. Okay, let's take a look at this. So in this case, we have f1 is equal to e to the x sine of x. G of x is e to the x cosine of x. And we want to think about if they're linearly independent or not. Well, here you see if they were linearly dependent, which is the opposite of being linearly independent, then we would be able to write down the following: that f of x is some constant times g of x for every x. But let's see what that means. See, that means that in fact we would have to have e to the x times the sine of x is equal to some constant times e to the x times the cosine of x for every x, for every value of x. That's what this means here, for every x. So what does that mean? Well, let's see. Let's just divide by e to the x times the cosine of x. See, but that would then mean that the sine of x over the cosine of x is a constant for every x. But see, that's not the case, because we know that the sine of x over the cosine of x is actually the tangent function. So the conclusion is that, in fact, there is no such c. So the fact that there is no such c means that these functions are linearly independent. Okay. All right, next example. Now, a very powerful fact, we'll call it a fact, but it's a theorem about these equations, is given in this theorem from our book. Let me see what the theorem is called here. The existence and uniqueness theorem guarantees the existence of these solutions. The one that I'm looking at is this following thing here. Here we go, Theorem 5. So they talk about the idea of the characteristic polynomial or equation associated with a differential equation, and here's the amazing fact that, well, it goes like this. So if you start with a linear differential equation, homogeneous, as I've stated, as I've written here, this is problem number 40, and if you're trying to solve this equation, then it turns out that we look at something called the characteristic equation associated with this differential equation. Okay? And I've written that right here. So notice what we do is we think of in our minds, well, we think of the y double prime. Rather than y double prime, we have some indeterminate squared minus 12 times this indeterminate plus 4 times, well, nothing that's not supposed to be there. Let me erase that. So just 4, it's gone. Okay? Or you can think of it as y to the 0 power. That is equal to 0. So what we do is we try to find the roots of this characteristic equation. So I wrote down I kind of like this technique, but it's very strange. So I must find the roots of this equation right here. Okay? And I'm going to do it in what I call a very strange, yet I think a nice way of doing it. So here's what I do. I say, okay, so we have this A. So you might want to look at this. It's kind of interesting. We have A, which is equal to this quantity, 9r squared minus 12r plus 4. Okay? So that's right there. I make this nice substitution. I say, all right, forget it. Let's not think of r. Let's suppose that r is x over 9. And I plug it in there, okay, which gives us now that, what I'm looking at here, that basically a is equal to 9 times x squared over 9 squared minus 12x over 9 plus 4. And then what I say is, okay, let's, here, I'll tell you what's going on here. Let's multiply both sides of the equation by 9. Well, if I do that, then I end up with this equation right here, that 9 times a, right, has to be equal to x squared minus 12x plus 36. And then, so then 9a, I'm writing it again here, I can now easily factor in this example to be this perfect square here, I guess. Because, you know, by this little trick, this little substitution has allowed me to get rid of this pesky leading coefficient, okay? That's why I do that. All right, and then what happens next is I realize that I'm going to resubstitute. See, I'm interested in the solutions for r. So I know now that since r is x over 9, that means that x is 9 times r. So right now I'm just really in here, I'm just like plugging in 9r. And then I'm going to divide both sides by 9. And if I do that, I'm going to move one of the 3's in here, giving 9, then 9r minus 6 becomes 3r minus 2. And the other 3 in here, when I divide, which makes 9r minus 6 equal 3r minus 2. So what we find is, in fact, that we have repeated roots. So we have the first root of this solution to this characteristic equation is r is equal to 3/2. But in fact, it's identical to the second root, which is r is equal to 3/2. So in this case, we have theorem 6, I guess, which tells us that the general solution is then given right here. Okay, so there I've done 3 problems which are similar to the problems I've asked you to do in the textbook. I will do the next section. I'll talk a little bit more about the Wronskian, okay, which they talk about a little bit in this section, I believe. Or do they? Or they just talk about Wronskian's solution? Oh, the Wronskian itself. So I'll talk a little bit about that in the next lecture. So I hope this helps you get through the homework in the first section, and I'll make another one here for the next one, and we'll keep rolling. Hope you did well on the test. Thank you. Bye.